Okay, so next we have Sriram, who's going to be talking about generation and amplification of primordial gravitational waves and a bit of inflation, right?
Yes. It's a pleasure to be giving this talk at this meeting organized to celebrate Bala's contribution to gravitational physics. I should thank the organizers for inviting me to give this talk. I'm going to talk about the generation of gravitational wave during inflation and their possible amplifications due to non-trivial phenomena, largely during inflation, and how this amplification can lead to levels of detection, to gravitational strength of gravitational waves that can possibly be detected by the ongoing or future interferometric detectors. I have divided my talk into two parts. One I would refer to as vanilla slow roll inflation, where the strength of the gravitational waves is essentially determined by the inflationary scale, and if it is very small, the strength of the gravitational waves will remain small, and the inflationary potential is smooth. It will not permit any non-trivial dynamics, and therefore the strength of the gravitational waves at very small scale corresponding to the interferometric observatories will also remain small and therefore will remain undetectable. The second part is what I would call as inflation with toppings. You can introduce features in the primordial spectrum such that their amplitude on the CMB scales remain consistent with the Planck and other data, while at small scale their amplitude can be enhanced and lead to levels of gravitational waves that are possibly detected, that can be detected by the future missions. And I will just summarize, and the summary will be evident. Let me start with slow roll inflation. The challenge is as follows. There are many inflationary models, and what I will essentially argue is that detecting the imprints of tensor perturbations can considerably help in achieving this goal. This is evident. This has been stated many a time. I strongly believe this. In the absence of detection of primordial tensors, we are going to have a multitude of inflationary models which will remain consistent with the data. Let me say a few words about primordial inflationary gravitational waves. The strength of the tensor amplitude is essentially determined by the Hubble scale during inflation, which through the Friedmann equation is determined by the potential in slow roll inflation. And it's also characterized, Souradeep kept talking about just 6 parameters. Well, he has essentially thrown away the tensors, okay, which is what we are trying to detect. And it's also characterized by this tensor spectral index, which in slow roll inflation is always negative, which means it's always red tilted. So on the CMB scales, if you have some strength on interferometric scales, they will be even smaller. In fact, you should understand as you go at later and later times during inflation, epsilon 1 keeps growing larger and larger, and the end of inflation is 1, and therefore it'll be red and further red tilted in slow roll inflation. And if you get to see the so-called consistency relation, the relation between the tensor-to-scalar ratio and the tensor spectral index, then you can convince yourself you have inflation driven by a single field. Because in multi-field models, this consistency relation will be broken. What are the current constraints? As you may know from the Planck data, you are talking about upper bound on the tensor-to-scalar ratio of about 0.06 or so. So many of the models that are being thrown out today, you should understand, is essentially because of this upper bound on the tensor-to-scalar ratio. For instance, like this, quadratic potential, for instance, and the lambda phi 4, which is somewhere here, all are being ruled out because of the stronger and stronger constraints on the tensor contributions to the CMB anisotropies. What does detection of the tensor perturbations imply? As is well known, it immediately allows you to determine the scale of inflation. At this stage, the R less than 0.06 corresponds to something like, V power 1/4 of about 10 power 16 GeV, or H by M Planck of about 10 power minus 5 or so. Now, the challenge is as follows. We started with such constraints about, this is somewhat old figure. So you're talking about something like 0.06 or something somewhere here. And what theorists have been able to construct is models which essentially will satisfy the current constraints on NS of about 0.96 or so and lead to smaller and smaller tensor-to-scalar ratio. One such popular model is called the alpha attractor, which pushes down essentially along the lines of the Saribinsky model, which appeared here, and it pushes it down to very small values of tensor-to-scalar ratio. In other words, there always exist models which can ensure tensor-to-scalar ratio beyond the upper bounds. If you get to see the tensor-to-scalar ratio, if you detect primordial tensor modes on the CMB scales, then you can check, for instance, this is the hope with, I think, core or light bird, that if you get to see the tensor-to-scalar ratio at 0.01 or so, then you can also check the consistency relation, and you can examine whether inflation is driven by a single field model. And it can also allow you to strongly constrain the slow roll parameters, which in turn allows you to understand what are the different reheating mechanisms. There may be models like the Higgs inflation and the Saribinsky inflation, which are degenerate. If you don't get to see tensors, but if you get to see tensors and thereby arrive at strong constraints on the slow roll parameters, it will allow you to actually discriminate between these models, which essentially point to different levels of reheating. This is on CMB scales. On large scales, we are interested in this quantity omega GW. I presume all of you are familiar with it. And what is the current constraint? Well, you have the constraint somewhere here. If you have a simple slow roll inflationary model, like the popular quadratic potential or the Saribinsky model, you will have predictions on these large scales, on these small scales, which correspond to the interferometric scale, frequencies. Then you will have slow roll inflation will lead to extremely small values, and all the current constraint from LIGO essentially points to something like this, and it corresponds to a tensor-to-scalar ratio of about 10 power 6 or so, upper bound or tensor-to-scalar ratio 10 power 6 or so on these scales. In other words, it doesn't allow you to constrain slow roll inflationary models. The question is, are there models, which can sort of increase the strength of these gravitational waves above and, reach observable levels at the interferometric scales? These correspond to inflation with topics. What it means is that you cannot have a simple slow rolling inflationary model. You need to introduce some features in your inflationary potential, or I shall argue, you need to introduce additional fields which have become popular over the last few years, where you have additional gauge fields, and if there are gauge field presence, they will have anisotropic stresses. They can increase the amplitude of these gravitational waves on small scales. And I will discuss two such scenarios here. One is when you have very strong scalar perturbations, stronger than the Kobe normalized amplitude, say on small scales, then what can happen is that at the second order of the perturbations, at the leading order, the scalars and tensors evolve independently, but at the second order in the perturbations, the scalar perturbations will pick up anisotropic stress, and they can end up contributing to the gravitational waves. And this is what has been shown. This is what you would have produced in a typically in a quadratic potential with no second order contributions. But if you take into account the second order contributions, you can have a spectrum which is like this, omega GW. But this is on very large scales, and I will just show you what happens on much smaller scales corresponding to the interferometric scales. So I have taken a few power spectra. What has been done is that we have introduced some features in the primordial spectrum on small scales. I haven't bothered to explain how these are generated during inflation. One can construct sometimes natural, sometimes peculiar inflationary models, which will lead to, say, a spike or a step or some features like this. And you can ask, what are the corresponding imprints on omega GW on small scales? And what you have is something like this. It actually peaks, at scales correspond where the PTA are sensitive to. And what has been done is that these have been increased by hand so that the F, the fraction of primordial black holes that have been formed is actually unity. In other words, the strength of very large and hence actually ruled out, and they will lead to substantially large values of omega GW on small scales. The other possibility is, and for instance, there are two constraints that arise on primordial spectra with features, they will end up leading to large levels of primordial black holes. There are already constraints that exist on them. You can use those constraints, and the current upper limits on which I had shown from LIGO, for instance, can be used to arrive at the following constraint on the primordial scalar power spectrum. And what you find is that you still have considerable room. For instance, these are the CMB scales corresponding to Kobe normalization of about 10 power minus 9 or so, but at small scales, you can boost by a factor of few orders of magnitude, and they will still remain, I'll be able to finish in time, okay? So, and they will still remain consistent with the data. There is another way of boosting the amplitude of the gravitational waves on small scales, and this, as I mentioned, is due to gauge fields. And you would know that, in the context of inflation, the modes oscillate when they are inside the Hubble radius, and their amplitude freeze once they leave the Hubble radius. And this is true for tensor perturbations, scalar perturbations, and also for electromagnetic modes. What I have plotted, are electromagnetic modes when there is no parity violation, and then there is parity violation. And this vertical line corresponds to the scale when the modes leave the Hubble radius during inflation. The x-axis is the number of e-folds. For instance, these modes leave the Hubble radius at 20 or so. 20 e-folds or so, counted from some given point. They oscillate inside the Hubble radius and they freeze on super Hubble scales. But if they violate parity, what happens is that around the time they leave the Hubble radius, one of these modes are amplified much more than the other. And in fact, these amplified modes can considerably enhance the amplitude of the magnetic fields during inflation, and they can lead to magnetic fields of observable strengths today, for instance. What does it do to the scalar perturbations and tensor perturbations? And this has been explored in a particular model, and they can boost your scalar perturbations in this fashion. It is highly model dependent because it depends on the coupling between the electromagnetic field and the scalar field. And for instance, here you have the Starobinsky model, conventional Starobinsky model, which would have produced a scalar power spectrum roughly like this, Kobe normalized spectrum, which will be boosted by the presence of these additional gauge fields. And they will also produce, because of the anisotropic stresses that they induce, higher levels of gravitational waves such that they may be possibly be detected by PTAs, LISA, or LIGO. So the only way you can have gravitational waves of adequate strength on small scales is to due to two effects, due to sharp features in the primordial spectrum, which can also lead to non-Gaussianities and which can also enhance these levels of gravitational waves, or you can have gauge fields. If you're thinking about conventional, simple, slow-roll inflationary models, and in the conventional picture where gauge fields don't play a significant role during inflation, the effects on small scales will not be significant. Therefore, I conclude with this summary. The detection of the imprints of the primordial tensor perturbations at large as well as small scale seem essential to unravel the physics operating at inflationary energy scales. If you just end up with upper bounds, you're going to end up with a lot of models which will remain consistent with the data, and theorists will go on to construct further models which will, one ensures that they remain consistent with the data. A detection on small or large or small scales would be ideal to understand what happened during inflation. I'll stop here. Thank you.